projects.
Hello everyone, I'm Li Xi from Warm Cloud, and I didn't make this presentation, so this presentation comes from Professor Lin Fang, but he's not be able to come here, so I'm presenting him to give this presentation. So as we can see, Lin Fang comes from Huazhong University of Science and Technology. This is a cooperation work. A lot of organizations collaborated together on this project, and DDL or Warm Cloud worked a lot on this project, but at the same time, JGU, which is a very good university in Germany, they collaborated in this project too, and professors from HUST, which is a Chinese university, collaborating to that too, and we managed to submit a paper to SC this supercomputer conference this year, and it is accepted. This talk will cover a lot of things about PCC. So I will introduce the background and the design, the implementation, and I will show some performance that Professor Lin Fang has got. So the background is, we know that Lustre has a lot of hierarchical storage. We have memory, we have SSDs, NVRAM, and we have HDD as the traditional storage. So it is a hierarchical storage system. So if we look into the HPC centers, we will see different tiers in different levels. For example, on the computer nodes, we will see NVRAM as the storage type, and we will see a lot of HPC center use our folding nodes between the computer nodes and the parallel file system. So usually people call that as a bus buffer, and of course we will use Lustre or other file systems as a parallel file system or the major storage, and below that we will use object storage or tape or DVD for archive. So as we can see, there are multiple storage tiers. So in that architecture, in that structure, we will face a lot of problems. The first problem is how we can get the best performance with acceptable budget or acceptable cost. And then another thing is we can see there are a lot of cache levels, how we can use those cache efficiently to get the best performance possible. And at the same time, when we design a system or a feature, we need to make sure that it is easy to use. So it is very important to keep the data consistency and keep the interface simple. And we want to make sure that the feature is as transparent as possible to the applications. So it would make it much simple for the applications to use these new features. When we start to write the paper, we investigated a lot of existing works, and there are a lot of similar ideas, but apparently they are all different with PCC. Some are close, some are not close. But I think some of the ideas in PCC is still novel, even so we can see a lot of similar ideas. So one similar idea is FS cache. It is relatively used a lot, but it is read-only cache, which is not the same with PCC. And another thing we see frequently is burst buffer. There are a lot of different implementations. But it is not the same with PCC too. So PCC is, if we look into the architecture of Lustre, we will see that it is on the client side, and that's one of the major difference with other cache levels. So as we have introduced, there are a lot of burst buffer implementations. So burst buffer is kind of the middle layer between the parallel file system and computer nodes, right? So all of the I/O will go into the bus buffer first, and it will flash into the parallel storage from time to time. So another solution or other solutions, some of the other solutions are on the server side. It means on the parallel file system or on the storage side. And that means it is a little bit far from the computer nodes, and you need to go through the computer networks to access the storage. But PCC is different. It is right in the computer nodes. You can set up a PCC storage in the computer nodes, and it is very close to the compute. So that means you can move your data as close as possible to the compute, and it will accelerate the I/O as much as possible. So that's a major difference, or the major with the other technologies. And of course, it uses a lot of internal mechanisms of Lustre. For example, DRM, Lustre log management is used a lot in this mechanism, and also it uses Lustre HSM. So as Andreas has said, it is kind of a reverse usage of HSM. So it reuse a lot of things in Lustre HSM, and it reuse the way how HSM copies the data. It uses the copy tool to synchronize from PCC to the OSTs. So we don't invent everything from scratch, and that saves a lot of effort. So the major ideas is we want to build another tier in the computer nodes, and we call that PCC. And that storage is usually based on quick quick storage like NVMe, NVRAM, or SSD. But at the same time, we want to make sure that the interface is simple. So we provide a same namespace with a global Lustre file system. That's important because otherwise it is hard to manage. And also, because of this cache, we can reduce the latency and log conflicts, and we can reduce the pressure to the OSTs because some of the IOs will be totally cached in the PCC level. Yeah, so if we look into some of the details, we know that some of the cache will be cached on the PCC. Some of the data will be cached on the PCC, but the other files might use the same I/O path of Lustre. So it depends whether the files has been attached to the PCC storage or not. So for the files that has been attached to the PCC, you will use the I/O path in the right side, and it will go directly into the cache I/O path, and it will access data directly from the for example, NVRAM. But for the other files, the data will be accessed from through the original Lustre I/O stack. And as we can see, there are obvious difference here. The cache I/O will be quick, both because the storage will be quicker and the network will be quicker. And at the same time, the I/O stack is much simpler than the Lustre stack, and it doesn't have a lot of network latency. So the implementation, I'm not going to introduce a lot of details here. If you are interested in that, you can check tickets in Jira or the paper. So basically, what we need to do is, if we want to cache the data onto the PCC, we need to do a step like attach the data into the PCC. That could be automatically version the data by, for example, defining a tool in your job scheduler, or do that manually. At the same time, if multiple class if multiple clients access the data remotely from the PC storage, there will be a restore step to get the data from the PCC, to flush the data from the PCC to OST to make sure that the data will be accessible from the remote clients. There are two modes for PCC. One mode is read-write, and the other mode is read-only. So there is some internal difference between these two modes. And the I/O flows are similar, but there is some difference here. So another thing that we are working on is the rule-based PCC, PCC data management. So we can define rules to check whether we want to cache the newly created data in PCC or not. So I think it is going to be very useful for us to easily manage the data we want to cache on PCC. And also, we are looking into the local quarter limitations to make sure that that users won't abuse PCC. And also, there are a lot of mechanisms related to PCC data management. So, for example, policy engine, you can use policy engine to manage the data movement between PCC and the original OST storage. And you can use changelog to analyze I/O patterns and to decide whether you want to prefer the data into the PCC or not, according to these analyze. And you can decide whether you want to effect the data from the PCC by maintaining an LRU or by checking whether the size is too big or not. I think one of the very important things in these slides is Professor Zhang and his college has been working on some performance test. And it is not on the original SSD. So we can use different storage for PCC, but NVRAM is a new storage, so everyone is looking into that. And the professor managed to do some simulation of PCC on top of NVRAM. It is not actually a VRAM, but it is a simulation based on the memory, but with some tunable parameters, and these parameter values are well accepted by the research organizations. So as we can see, what they do is to use both SSD and NVRAM as PCC storage and compare whether there is any difference between these two kinds of storage types. I think I need to introduce a little bit about what's the meaning of each line here. So the Lustre means the original Lustre performance if the data is located on the OST. And the SSD LPCC, which is the red one, it means that you cache your data onto the PCC storage, and the PCC storage is SSD. So the SSD is not super fancy. So the performance is reasonably good, but not so good. But the other four lines are PCC on top of NVRAM, but they use different file systems. So the green one use EST4 file system without any special feature for NVRAM. The purple, I think, one use the DAX feature of EST4. And PMFS LPCC means you use LPCC, but at the same time you use PMFS as a file system to format the PCC storage. So another well-known NVRAM file system is Nova. So there is a line for Nova LPCC2. So PMFS is the other well-used file system which is designed and implemented especially for NVRAM. So as we can see from these lines, so of course, LPCC can improve the performance, but we can see a very huge difference between these lines too, because, for example, the LPCC based on EST4 but without DAX, the performance is higher than the LPCC on top of SSD, but it is much lower than the performance on NVRAM, but with EST4 using DAX feature. So the DAX feature will enable you to skip the page cache, and that will reduce a lot of latency. And so we can see there are a lot of performance difference between the file systems that are designed or optimized for the NVRAM and the file system that do not optimize for NVRAM, even so the storage type is the same. So we can see we can get similar results from the read performance of IOPS. But one thing interesting is the EST4 with DAX feature. So as we can see, if the I/O size is small, I mean one kilobytes, we can see that the EST4 PCC with DAX feature, the performance is even slower than the EST4 without DAX performance. So I don't know in details because I don't know the DAX feature a lot, but I guess there might be something that could be improved in the DAX implementation of EST4. But the PMFS Nova always has the best performance because they are designed for NVRAM. So we can see the similar things for the latency. So the Lustre obviously has higher latency, right? Because the storage and the network, and Nova and PMFS has very little performance, very little latency. Sorry, and we can see that we can get similar conclusion from the client, from the single client write performance. I mean, this slide is bandwise, but at the same time, if we look at the line of EST4 with DAX feature, we can get similar conclusion here. Even so, if the I/O size is high, when the I/O size is big, the DAX, the EST4 with DAX feature has good performance comparing to the EST4 without DAX. But when the I/O size is small, the performance is bad. It's pretty bad because it is even worse than the SSD. So we can see similar results for the write performance of throughput, and also the write performance for latency. And another benchmark that Professor Zhang has done is to run different workload of file bench on different kind of storage. So the last means, as we said, means saving the data into the OSTs with normal storage. The SSD LPCC means that we use EST4 and use SSD as a storage for LPCC. But the NVRAM LPCC means they use Nova file system and use the NVRAM as a storage type. So we can see the performance is improved when you use LPCC. But at the same time, if the storage type is different, the performance is different too. So yeah, if you use NVRAM, the performance is much better than SSD. So another thing they do is to run some scalability test. When the number of clients increase, the aggregated bundle-wise increase too. So this is the right scale test. We can get a similar performance number. And when the dataset size increase too, we can see that we can get similar conclusion that NVRAM-LPCC can increase the performance a lot, even on top of SSD-LPCC. That's the expected result. And when the number of clients increased, the read-only PCC has bundle-wise that increased almost linearly with number of clients. So if we try to get some conclusion from these slides, we can see that the performance can be improved a lot from the PCC if your application, if the I/O patterns of your application is well suitable to run LPCC. And at the same time, we can get some details from the benchmarks. For example, we know that the backend file system of LPCC is very important if you are using NVRAM. So we need to run benchmarks to make sure we choose the right NVRAM file system for PCC. And if you and as a conclusion is obvious, if you have budget, you should always use NVRAM for PCC because it improves the performance a lot. Okay, that's all. Any questions?
You have some questions about the...
On your bandwidth graphs, you had the Lustre, plain Lustre was kind of constant going across the bottom there.
Right.
Yeah, and basically no matter what the block size was, but that's...
Right.
I mean, traditionally we see significant changes in Lustre's performance based on the block size, so I'm kind of wondering how that is it normalized or something to 1 somehow?
I don't know whether there is any, so how to say, the numbers here is pretty small, so I think there might be some difference between, for example, 1K and 4K, and we are unable to find that because it is too small here. Maybe there is 20 or 30% difference, but we are not able to see here. But that's my guess because I don't have the original data and I'm not engaged in this benchmark.
Other questions?
Not sure if you mentioned it, but I was wondering if you have a cache coherent model.
So what model?
Cache coherency. I mean, if you have this LPCC, this client on top the Lustre client, as I understand, so you can cache the data persistently in the RAM. But I was wondering if you have another client who's also wants to access the same file.
Right.
So you have a coherency model?
So if another client accesses the same file, it will use the internal mechanism of Lustre to how to say, flush the data.
Yeah, you have to synchronize then.
Right. So it is like the mechanism of HSM. So in HSM, when you access the data, you will need to restore the data from the HSM storage. But PCC is using the same mechanism, but in the reverse way. So it will needs to flush the data from the PCC storage to the OST. And after that, you can you can read the data from the OST in the remote client.
Okay, that means at that point, when one client is modifying the data, then it's flashed to the back end.
Right, sure.
Ah, okay.
Yeah.
Thank you.
So then, okay.
Yeah.
Okay, thank you.
Thank you.